The United States Geological Survey recorded 847 earthquakes beneath Yellowstone National Park in the month of July 2026 alone. Not 847 seismic events across a year or across a decade of gradually building activity. 847 earthquakes in a single month in the specific underground geography of the Yellowstone caldera, the largest supervolcanic system in North America and one of the most geologically consequential volcanic systems on the planet. The monthly earthquake total for July 2026 represents the highest single-month seismic count recorded at Yellowstone since comprehensive modern monitoring began in the 1970s, exceeding the previous record set during a significant earthquake swarm in 2009 by more than 200 events. 847 earthquakes in 1 month. And the USGS's official volcanic activity notice level for Yellowstone remains at normal, the lowest category on the 4-level scale that runs from normal through advisory, watch, and warning. That specific combination, a record-breaking seismic month and an unchanged normal alert level, tells you something important about both the science of volcanic monitoring and the genuine complexity of interpreting what is happening beneath one of the most studied and most consequential geological systems in the world. It is not evidence that the USGS is hiding something. It is evidence that the relationship between earthquake activity and volcanic eruption probability is more complicated than headlines about shaking like never before typically suggest, and that understanding what is actually happening at Yellowstone requires the kind of careful, specific analysis that the record-setting numbers deserve. It is August 18th, 2026. Let's build a complete and honest picture of what is happening beneath Yellowstone, what the earthquake swarms mean scientifically, what they do not mean, and why this genuinely remarkable geological situation deserves the serious and accurate attention it is receiving from the scientific community, even if the alarm level has not changed. Start with what Yellowstone actually is, because the word supervolcano is used frequently in coverage of this situation without always being accompanied by a clear explanation of what the term describes and why it matters for understanding the scale of what the USGS is monitoring. Yellowstone sits above a geological hotspot, a plume of abnormally hot mantle material that has been burning through the North American tectonic plate for approximately 16.5 million years as the plate has moved southwest relative to the stationary hotspot. The result is a chain of ancient volcanic calderas extending from the Snake River Plain of southern Idaho eastward to the current Yellowstone caldera in northwestern Wyoming. The hotspot has not moved, the continent has moved over it, leaving a trail of ancient volcanic scars that record the hotspot's geological history. The Yellowstone supervolcano is not a classic conical volcano like Mount Rainier or Mount St. Helens. It is a caldera, a massive collapsed depression created when previous eruptions were so large that they emptied the magma chamber beneath them faster than the overlying rock could be supported, causing the surface to collapse inward. The Yellowstone caldera measures approximately 45 by 30 miles, making it large enough to contain an entire city within its boundaries. Yellowstone National Park exists largely within and around this caldera, and the geothermal features that attract millions of visitors annually, the geysers, the hot springs, the mud pots, the fumaroles, are all surface expressions of the extraordinary geothermal heat that the hotspot continues generating beneath. The geological record of Yellowstone's eruption history documents 3 major caldera-forming eruptions. The most recent occurred approximately 631,000 years ago. The previous one, approximately 1.3 million years ago. The one before that, approximately 2.1 million years ago. This roughly 700,000-year recurrence interval has generated significant public interest in the question of whether another major eruption is overdue, given that 631,000 years have passed since the last one. The overdue framing, while understandable, reflects a misunderstanding of how volcanic systems work. Volcanic eruption recurrence intervals are not clocks. The roughly 700,000-year interval between Yellowstone's 3 major eruptions represents an average of 3 events, which is an extremely small sample size for statistical inference about future timing. More importantly, volcanic systems erupt when geological conditions are right for eruption, not on schedules. A volcanic system that last erupted 631,000 years ago is not more likely to erupt tomorrow than it was 100,000 years ago, because the geological processes that drive eruption, primarily the accumulation of sufficient magma at sufficient pressure in the system's shallow magma reservoir, operate on their own timescale that does not reference the time elapsed since the previous eruption. Now let's talk about the current earthquake swarm specifically, because understanding what is generating 847 monthly earthquakes beneath Yellowstone requires understanding the mechanics of seismic activity in a volcanic system. Yellowstone experiences between 1,000 and 3,000 earthquakes per year under normal conditions, averaging roughly 80 to 250 per month. The July 2026 total of 847 exceeds the high end of this normal range by approximately 3 to 4 times, placing it statistically in the category of a significant earthquake swarm, the geological term for a cluster of earthquakes that occur in a relatively short time period in a geographically concentrated area. Earthquake swarms at Yellowstone are not uncommon. The system has experienced thousands of them throughout the monitoring record, including several dozen swarms that exceeded 1,000 total events when tallied across longer periods. What makes swarms useful scientifically and concerning in a monitoring context is not their existence, but their specific characteristics, the depth at which the earthquakes are occurring, the magnitude distribution of the events, the spatial pattern of earthquake locations, and how these parameters change over time. The July 2026 swarm has produced events at depths consistent with activity in the upper crust above the primary magma reservoir, between approximately 2 and 8 kilometers below the surface. This depth range is where hydrothermal fluid movement, tectonic stress adjustments, and the mechanical interaction between rock and the pressurized fluids in Yellowstone's extensive hydrothermal system produce most of the system's routine seismic activity. The depth distribution of the July events is not primarily consistent with magma movement toward the surface, which would be expected to produce earthquakes at shallower depths as magma pushed into the upper crust. The magnitude distribution of the July swarm shows the typical pattern of volcanic earthquake swarms, with the vast majority of events in the magnitude 0 to 2 range, detectable by sensitive seismometers, but imperceptible to humans without instruments. The largest single event in July 2026 reached magnitude 3.4, generating minor shaking at the surface and providing the kind of perceptible ground motion that tourists in the park area could feel. Magnitude 3.4 is not a geologically significant earthquake in terms of damage potential. It is, however, a notable event in the specific context of the swarm's development because of what it tells seismologists about the stress state of the rock in that specific location. Now let's talk about the specific monitoring architecture that USGS and the Yellowstone Volcano Observatory use to track the system's behavior, because understanding how the science works is essential to understanding why the alert level remains at normal despite the record seismic month. The Yellowstone Monitoring Network includes approximately 30 seismograph stations deployed across and around the caldera that provide the earthquake detection capability at the heart of the monitoring program. These stations are supplemented by a GPS deformation monitoring network of approximately 15 continuously operating receivers that track ground surface movement at millimeter scale precision, a critical measurement for volcanic monitoring, because magma accumulation in the shallow system typically produces ground uplift as the magma inflates the reservoir like a balloon expanding inside the rock. The deformation data is where the July 2026 situation becomes specifically interesting for scientific analysis. The GPS network shows that the Yellowstone caldera has been in a general subsidence pattern, meaning the ground surface is slowly settling downward rather than inflating upward since approximately 2015. This subsidence is associated with the gradual cooling and degassing of the hydrothermal system and the shallow magma reservoir, processes that reduce rather than increase the likelihood of an eruption in the near term. The July 2026 earthquake swarm has not been accompanied by a reversal of this subsidence pattern toward uplift. Ground deformation remains consistent with subsidence. This is the specific observation that most directly justifies the maintained normal alert level. In volcanic systems, the combination of significantly increased seismicity and ground uplift is the paired signal that indicates magma is being added to the shallow system in amounts that are changing the mechanical state of the rock above the reservoir. Significantly increased seismicity without accompanying ground uplift is more consistent with the hydrothermal system being the primary driver of the activity, with fluid pressure and movement through fracture networks, producing the earthquakes through mechanisms that do not require magma movement toward the surface. The hydrothermal system at Yellowstone is one of the largest and most active on Earth. The system contains approximately 10,000 individual hydrothermal features and circulates enormous volumes of water that has been heated by contact with rocks that are themselves heated by the underlying magma system. This hydrothermal system is capable of generating significant seismic activity through multiple mechanisms: thermal fracturing as hot fluids encounter cooler rock, pressure changes as fluid pathways are opened or closed by small earthquakes, creating feedback loops, and the mechanical stress produced by the seasonal and longer-term variations in the hydrothermal system's circulation patterns. The July 2026 earthquake swarm is currently best characterized as consistent with elevated hydrothermal system activity, rather than magma movement toward the surface. That characterization could change if the deformation data begins showing uplift, if the earthquake depths migrate shallower, or if specific seismic signal characteristics indicating magma involvement appear in the data. None of these changes have been observed as of August 18, 2026. Now let's address the big question that the record seismic month inevitably raises, which is what a major Yellowstone eruption would actually mean, because understanding the genuine scale of the potential consequences is part of why the system receives the monitoring attention it does regardless of the current alert level. The three major caldera-forming eruptions in Yellowstone's geological history were among the largest volcanic events in the geological record of the past few million years. The most recent, approximately 631,000 years ago, ejected an estimated 1,000 cubic kilometers of material, roughly 2,500 times the volume ejected by the 1980 eruption of Mount St. Helens, which was itself one of the most significant volcanic events in American history. An eruption of this scale would deposit several meters of volcanic ash across much of the western United States, with measurable ashfall extending across most of North America. The immediate region would experience pyroclastic flows, fast-moving avalanches of hot volcanic gas and rock that would make the area within roughly 100 miles of the caldera immediately uninhabitable. The ash fallout would disrupt agriculture across a vast area, with the specific timing of an eruption relative to growing seasons determining the extent of crop damage across the Great Plains, America's primary grain-producing region. The global climate effects would be significant. Major volcanic eruptions inject sulfur dioxide into the stratosphere, where it converts to sulfate aerosols that reflect sunlight and can produce measurable global temperature reductions for periods of 1 to several years. The 1991 eruption of Mount Pinatubo in the Philippines produced a global average temperature reduction of approximately 0.5 degrees Celsius for about 2 years. A Yellowstone-scale eruption would likely produce significantly larger climate effects over longer time periods, with consequences for global food production that would extend well beyond the direct impact zone. These consequences are real and scientifically documented in the geological record of previous supereruptions globally. They are also consequences of an event that is not currently indicated to be imminent by any of the monitoring data from the system. The geological record and the monitoring data both deserve to be discussed honestly and completely, which means discussing the scale of potential consequences while also being clear that nothing in the current monitoring picture indicates those consequences are approaching on any human-relevant timescale. Now, let's look at what the hydrothermal system itself can produce independently of any major magmatic eruption, because Yellowstone poses a range of potential hazards that span from the immediately concerning to the existentially consequential, and the current activity is most relevant to the middle of that range. Hydrothermal explosions are a specific Yellowstone hazard that does not require magmatic eruption, but can produce significant local effects. These explosions occur when superheated. Water flashes to steam faster than it can escape through the existing hydrothermal features, generating an explosive release of steam and rock fragments that can produce craters hundreds of meters across and eject material considerable distances from the explosion site. The Mary Bay crater on the northeastern shore of Yellowstone Lake, approximately 2.6 kilometers long and 1.5 kilometers wide, was produced by a hydrothermal explosion approximately 13,800 years ago. Hydrothermal explosions at this scale would be locally catastrophic for anyone in the immediate vicinity and would produce significant damage to the park's hydrothermal features and infrastructure. They are not planetary scale events, but they are genuine hazards that the current elevated hydrothermal system activity makes more relevant to near-term risk assessment than a major magmatic eruption. The USGS's normal alert level reflects that the current activity is not showing the specific indicators associated with a major magmatic eruption being imminent. It does not mean that all hazards associated with an active hydrothermal system are absent, or that the current elevated activity carries no risk at all. The monitoring system's value is precisely in making these distinctions with the specificity that data allows, rather than either dismissing all concern or amplifying it beyond what the data supports. Now let's look at the broader scientific context of the July 2026 swarm within the history of Yellowstone monitoring, because placing this record in its historical context helps understand both its significance and its proper interpretation. The 2009 earthquake swarm at Yellowstone, the previous record holder for single-month seismic activity, produced approximately 600 earthquakes in January of that year and significant media coverage suggesting an impending eruption. The eruption did not occur. The swarm was followed by a return to normal seismic rates and has been understood since as a significant but not unusual expression of the hydrothermal system's dynamic activity. The scientific response to the 2009 swarm improved the monitoring network's capability and produced better models for distinguishing hydrothermal from magmatic seismicity, models that are being applied to the interpretation of the July 2026 data. This historical context matters for calibrating the appropriate response to the current situation. Record-setting seismic activity at Yellowstone has happened before without producing either a major eruption or a significant escalation of the alert level. The scientific community's ability to interpret the current swarm is better now than it was in 2009 because the monitoring network is denser, the models are more refined, and the understanding of what specific signals indicate magmatic versus hydrothermal drivers has been substantially improved by research conducted in the intervening years. The current swarm is being monitored more carefully and more scientifically than any previous Yellowstone earthquake sequence. The data it is producing is being analyzed in real time by a monitoring program specifically designed to detect the transition from hydrothermal to magmatic activity if and when that transition occurs. The maintained normal alert level reflects the judgment of that monitoring program, based on all available data, that the transition has not occurred. Now let's look at what visitors to Yellowstone National Park should understand about the current situation and what, if anything, they should do differently in response to it. Yellowstone National Park receives approximately 4 million visitors per year. The current seismic activity has produced some additional ground shaking that visitors can occasionally feel, particularly the magnitude 3.4 event in July that was perceptible to people in the park. The Park Service has not issued any closures or evacuation recommendations related to the current seismic activity. The boardwalks and viewing areas around the park's hydrothermal features remain open and are appropriate for visitor use. The permanent guidance for visitors to Yellowstone's hydrothermal areas applies regardless of the current seismic activity level. Stay on designated boardwalks and trails. Do not approach thermal features off the maintained paths. Do not touch the water in thermal pools or geysers. These rules exist because Yellowstone's hydrothermal features are genuinely dangerous in immediate physical terms, with pool temperatures that can reach boiling and ground that can be thin and unstable near thermal areas. They are not rules that need to be amplified by the current seismic activity because they reflect permanent conditions of the environment rather than temporary crisis response measures. The appropriate response to the current situation for people who are not geologists or park managers is to be informed about what the monitoring data shows, to understand that the normal alert level reflects a scientific assessment rather than a decision to suppress alarming information, and to appreciate that monitoring programs like the one that identified and is characterizing the July 2026 swarm are exactly the kind of scientific infrastructure that responsible management of geological hazards requires. Now, the broader analysis of what the July 2026 swarm tells us about the state of volcanic monitoring and public communication around geological hazards. The 847 earthquakes in July 2026 are real, significant, and worth careful attention. The record-setting nature of the monthly total is a genuine scientific observation that the monitoring network is correctly flagging as requiring enhanced attention and analysis. The continued normal alert level is a scientific judgment based on the specific combination of seismic and deformation data that distinguishes elevated hydrothermal activity from magmatic activity approaching the surface. Both of these things are true simultaneously. The activity is genuinely elevated. The eruption-related indicators are not present in the data. Public communication about geological hazards struggles with exactly this combination, because the natural human response to record-setting numbers is to scale the alarm proportionally to how record-setting the numbers are. If July produced the most earthquakes ever recorded in a month, surely the alarm level should reflect the most elevated concern ever recorded. The scientific reality is more nuanced. The alarm level reflects what the data says about eruption probability, not what it says about seismic activity volume. High seismic activity in the absence of the specific indicators associated with magmatic movement does not indicate high eruption probability. This nuance is important for the public's ability to make informed decisions about their own engagement with geological risk, their support for the monitoring programs that generate this data, and their calibration of the difference between genuinely alarming geological signals and elevated activity within the range that a large, active volcanic system produces. America's most dangerous volcano is shaking like never before in the recorded monitoring history. The scientists watching it have the most sophisticated understanding of what it is doing and why that has ever existed for this system. What they are seeing is remarkable geological activity that does not currently show the specific indicators of an imminent major eruption, but that deserves exactly the intensive scientific attention it is receiving. Look up the USGS Yellowstone Volcano Observatory's weekly update reports. They are published publicly, written accessibly, and represent the most current and accurate assessment of what is happening beneath the caldera. The scientists who write them are watching the same numbers that are generating the alarming headlines, and they are providing the specific, data-grounded context that the numbers require to be properly understood. 847 earthquakes. In July 2026, America's most dangerous volcano is shaking like never before, and the scientists watching it are doing exactly what they should be doing. watching, measuring, publishing, and updating their assessment as the data changes. That is how geological hazard monitoring works when it works well. And right now, at Yellowstone, it is working well.